So good day, ma'am. I'm Michelle M. Mangpang, and my partner is Vince Randall Rustia, and we are the reporters of Week 11. So let's start. Solidification process. So what is solidification? Solidification is a phase transition which is liquid turns into solid when its temperature is lowered below its freezing point. Why to study in detail? The solidification of metals and their alloys is important in various industrial processes. Most of the components produced from the metals are by casting process. When a metal is welded, a small portion of metal near weld melts and resolidifies. So this is a diagram of solidification. Liquid, solid. Then here's the temperature. So during the solidification, the liquid changes into solid as cooling proceeds. The energy of liquid is less than that of the solid above the melting point. Hence, liquid is stable above the melting point. But below the melting point, the energy of liquid becomes more than that of the solid. Hence, below the melting point, the solid becomes more stable than the liquid. Thermodynamically, both liquid and solid have equal energy at melting point, and therefore both are equally stable at melting point. Freezing is the almost always the exthermic process, meaning that the liquid changes into solid, heat is released. This heat must be continually removed from the freezing liquid or the freezing process will stop. The energy released upon freezing is a latent heat and it's the entropy part. Some undercooling will be essential for solidification. Solidification occurs by two processes, the nucleation and the growth. So, the cooling curves. So, this is the diagram of the cooling curves. You can see the liquid phase, the solid phase, and the freezing point. Here, the time, and then this is the temperature. So, a cooling curve is a graphical plot of the changes in temperature with time for a material over the entire temperature range through which it causes total heat to be removed for solidification. And this is the formula for solidification. This is the cooling curve, this is undercooling. So, kato kaniya kay cooling curves, and this is the cooling curve for undercooling. So we can see the temperature, and this is the undercooling, the evolution of heat under the undercooling, and this is the time. So next is driving force for solidification. So solidification is undoubtedly the most important processing route for metals and the alloys. For a pure metal as the fusion temperature, and this is the formula. So So this is the nucleation. So the first step of the metal solidification is the creation of tiny, stable nuclei and the liquid metal. So cooling the liquid below its equilibrium freezing temperature or undercooling provides the driving force for solidification. Once a cluster reaches the critical size, it becomes a stable nucleus and continues to grow. The mold walls and the Na solid particles present in the liquid make nucleation easier though. So this is the kanang rotation for nucleation. First is the cluster of atoms, embryo, nuclei, crystals, grains. So back to the embryo, back to the cluster atom. So R means the critical radius. So nucleon nucleation is the volume freeze energy to freeze free energy difference between the liquid and the solid. So this is the formula of volume energy. So next is the surface energy. The energy needed to the create surface for the spherical particles. So this is the formula of surface energy. So specific surface energy are the particles. So this is the Y stands for specific surface energy for the particle. So next is total free energy changes. So this is the formula of energy change. At the low temperature, atoms from the small of of groups embryo form may either form into stable nuclei or may dissolve at the liquid. Beyond the critical radius of the nuclei, it will remain stable and growth occurs. So this is the diagram of nucleation. This the solid, the blue. So the solid, there are parts of liquid radius, and the radius is kanang sa tunga. So diameter is ana. Next is the nucleation. So this is the kanang diagram of nucleation. This is the formation of grains. So liquid, nuclei, liquid, the crystals that will form grains. So grain, boundaries, grains. So next types of nucleation. So nucleation has two types. So homogeneous nucleation. So what is homogeneous nucleation? Homogeneous nucleation is the formation of the critically sized solid from the liquid by clustering together or large number of atoms of high undercooling. So the next is heterogeneous nucleation. So this is the formation of a critically sized solid from the liquid on the impurity surface. Heterogeneous nucleation occurs in a liquid on the surface of its container. So insoluble impurities and other structural material that lower the critical free energy required to form a stable nucleus. In a practice, homogeneous nucleation rarely takes a place of heterogeneous nucleation occurs either or the mold walls or the insoluble impurity particles. So this is the types of nucleation. So nucleation are two types, homogeneous and heterogeneous. So this is the diagram of homogeneous and this is the diagram of heterogeneous. So the growth. Once solid nuclei form growth, of course atoms are attached to the solid surface. So growth is the physical process by which its new phase increases in size. In the case of solidification, this refers to the formation of stable solid particle as a liquid freeze. So nature of growth of solid depends on how heat is removed from the system. Sensible heat and latent heat is to be removed. The manner in which latent heat is lost determines the growth of machines. There are two growth mechanisms. So one is the planar growth, two is the dendritic growth. So the difference in planar and dendritic growth arises because of the different sink of the latent heat. So this is the growth diagram of the growth. The solid, the liquid, and the plus VE, the T gradient columnar growth, the solid, the liquid, and the T gradient. So first is the planar growth. The heat is dissipated through the crystal EI from the ground crystal is cooler than the melt. Here a solid bulge into the liquid would melt again because of the temperature in the bulge in the above theme. Therefore, one obtains a stable flat solidification front. So, any small protuberance that begins to grow on the interface of the surrounded by liquid above the freezing temperature. The growth of the protuberance stops until the remainder of the interface catches up with it. This planar growth occurs by the movement of the smooth solid liquid interface into a liquid. So dendri so dendritic growth. So what is dendritic growth? For a strongly undercooled melt by the heat of crystallization can also be dissipated through the melt. Under this condition, a small solid protuberance called a dendrite which forms at the interface encouraged to grow as the solid dendrites grow the latent heat of fusion is conducted into the undercooled liquid raising the temperature of the liquid towards freezing temperature. Dendritic growth continues until the undercooled liquid warms to the freezing temperature. Any remaining liquid in the solidifies the planar growth. These are the thermal dendrites different from dendrites in alloys. So this is the planar growth and this is the dendritic growth. So next is solidification defects. So shrinkage. Most materials contract to the shrink during solidification and cooling. Shrinkage is the result of three results. First is the contraction of the liquid as it cools prior to its solidification. Number two is contraction during phase change from the liquid to solid. Third is, and lastly, is contraction of the solid in the continuous to cool to ambient temperature. Shrinkage can sometimes cause cracking to occur the component as a solidifies. So, gas porosity. Many metals dissolve a large quantity of gas when they are liquid. However, when metals solidify, they retain only a small part of the gas, but these form bubbles trapped into the solid metal producing gas porosity. Next is the design consideration in casting process. So to minimize the damaging effects of shrinkage, riser is used to casting process. So what is riser? Riser is a reservoir of molten metal to composite of shrinkage. This molten metal is continuously available from risers to prevent shrinkage voids. It is desirable for the regions of the casting most distance from the liquid metal supply to freeze first and for solidification to progress from these remote regions towards the riser. Directional solidification is obtained by using shields. Also, to minimize shrinkage problems, with final cast product allowance is given for the size of mold during pattern design. So, for the conclusion of this report, principles involved in the solidification of metals have been only discussed. Third, a second is the solidification of alloys are much more complex and involves solute partitioning studies. The third and lastly is based on the solidification studies, design considerations were implemented in the casting process.